Well, hello, everyone. I think we'll go in and get started. Let me open up in prayer and I'll give you a sense of what we're going to be covering today. So, dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in this course. I pray that the material that we cover will be clear. Pray it's going to be instrumental for them as they're preparing their time here at APU or finishing up their time here at APU in their engineering or computer science or computer information systems program. Pray that you would help them in the times they've been able to study scripture, that you can help them to take that to heart, and pray that they can also see a path forward for having good ways of having theological understanding and be able to apply it to their life. Plus, give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Well, I think Tuesday went pretty well, and we get into this next major section of the material that we cover in class. And I also tried to personalize it a little bit, so both an engineering and a computer science point of view were brought into light for that. This is going to be a little bit harder to be doing that, but I'm hoping that as I get more information from you all, I can continue to be figuring out how to do that. So computer engineering, computer science, computer information system, I would say relates to these concepts that we've talked about in general. Time would be the one that's definitely has a good crossover. But in this particular discussion, we're going to be talking about length and length-related variables that occur in engineering and computing. And so I like to always think in general, just consider a cyber physical environment. And so with this one, we're going to be dealing it more with the physical side of that rather than how we would go about thinking of programming it or what have you. But this would be part of the business logic, if you will, some of the things that would be part of the app or the capability that you would be mindful of the characteristics of the physical world that you're connected to with your application. So in terms of chapter objectives, first we'll get better acquainted with length as a fundamental dimension. So we had this idea of what a meter was. We talked about that in our last lecture, and the standards of how the SI units and how France did a characterization of that as well as others. So this describes the role of length in engineering analysis and design as well as units, measurements, and calculations. We'll talk about the ratio of lengths, radians, and strain, and explain what is meant by radians and strain, both length-related quantities and the role in engineering analysis and design. So some of the things we're going to be touching on in this lecture, I know some of you are into mechanical engineering, and I think you'll be getting some positive feedback with the material that we cover here to give you some perspective on that. So length is a fundamental dimension, ratio of two lengths, and then area describe the role of area, a length-related quantity, engineering, analysis, and design, as well as its units, calculations, and measurements. And I'll try and include some practical ways in which we encounter that. And finally, we have volume, describe the role of volume, a length-related quantity in engineering, analysis, and design, as well as its units, calculations, and measurements. Finally, we'll get into this topic called second moment of area. And there's also another phrase for that is used, and I'll explain that in a little bit and explain what is meant by a second moment of inertia, a length-related quantity, its role in engineering analysis, design, and calculations. So let's think about length as a fundamental dimension. And so here we can be looking around our world. And how does this come up? So it's one of the 7 fundamentals or base dimensions that we use to properly express what we know of our natural world. We talked about that in our last lecture, and so now we're getting a little bit more specific one at a time. And so let's observe our surrounding. A soda can, for example, what are its dimensions? You can be thinking about that. Well, that's a volume question. And so we'll get a chance to get some exposure to that. What are the important design factors? how strong does that need to be, say for a soda can? And so that gets into the thickness of the walls of the can, what kind of lining, how are you going to open it, the size of a highway sign and related design factors. And so when you go get your driver's test, one of the things they do is they check your eyesight. And so I think it's 20/40 is what they're looking at as a minimum vision that would be necessary. So you think of a stop sign, how long it takes you to stop. And so there's the stop sign, the speed, rate of speed that's allowed in that area. Someone that's able to see at least 20/40. Those are all to be factors that you get into the size that a highway sign would have to be. The width of hallways and supermarket aisles. I had kind of an interesting experience of that. So I'm sure you guys have been to supermarkets or as well as department stores. And my wife and I, we went to the UK and they had a department store. We went there and the aisles were actually closer together and I could actually sense it. So there was a different way of how they were coming up what we thought that right size should be. Finally, there's a size of a car seat and how it's determined. Maybe that's something that you have some experience with. Maybe both perhaps an annoying thing is the size of a seat when you're flying in an airplane. It's not as wide or as comfortable as you would have for a car seat, but those are all examples of where length as a fundamental dimension starts to come up. Then we have coordinate systems. Coordinate systems are used to locate things with respect to a known origin. And so these are the names, and some of you, maybe all of you are familiar with this. Cartesian, you can think of like an X, Y, and Z. And cylindrical is you have, you can think of a soda can. It has that kind of a relationship in terms it's halfway between Cartesian and spherical. Two are linear and one is gives an angle. And finally, spherical is you just looking at the dimensions of a sphere as you go out. And those are three coordinate systems that you could encounter. So why would this be important? Let's think of a coordinate system. You're trying to get from your home to the bank. And guess what? You can't go this direct route. You're going to have to be obeying the going on the street. And if it's a one-way street, you're going to have to be aware of that. So here you would see a navigation, something on the order where you're going to go from one to another. And so that gives you an idea how you would be expressing that in coordinates, most likely the Cartesian for this type of application. Some of you will be programming various type of machinery that would be in some type of a production environment. And one of those tools is a computer numeric controller CNC machine. And so these can be useful for milling or having a lathe. And so you can get some very interesting and complex things that are put into a piece of wood, a piece of metal, or what have you. All of these are going to be things that are related to a coordinate system that you want to be able to get your understanding and utilize that. Depending on how accurate the measurement needs to be and the size of the object being measured, we use other measuring devices such as a ruler, a yardstick, and a steel tape, a tape measure. Well, I'm going to have an example come up a little bit later with survey equipment. You can think of another thing, another example of measuring, but it's using a different approach. So these devices are based on internationally defined and accepted units such as millimeters, centimeters, meters, inches, feet, or yards. In the last few decades, electronic distance measuring instruments, EDMI, have been developed. I remember when I was in my undergraduate, there was one of my students that actually got a patent and had a company that wanted to take his idea and make it reality. And so this is really can be quite nice, as you can have using a laser, it goes out and then comes back, and it can actually, by how long it takes, and it's measuring that time, it can figure out how far one point is from another. Well, something to be aware of. I think all of you have taken trigonometry. And so here are some useful relationships. I'm not going to go through these one at a time, but just like this first, if I was to draw a sine wave, and then if I was to square that, it means it's going to stay above the origin for both the up cycle and the down cycle. And sine and cosine are out of phase with each other by 90 degrees. So if you start to think about this, and these are for the same angle, you would see that that is always going to be, because of the contribution of these two elements, it's always going to be staying at 1. So any alpha along that wavelength, it would always be at that 1 based on those two contributions. So some of these by themselves may not be easy to figure out, but if you're trying to have some kind of algebraic expression that also includes some trigonometric elements, this could be a way of finding a solution that otherwise might be kind of difficult. I'll have a couple of videos in here, and so this is going to be the first one. Here was something I thought was interesting. There's something called the nominal size versus the actual size. And if you've ever been to Home Depot or Lowe's or something like that, and you try and buy a 2x4, and I'm showing an example of what this is, and it's actually not 2 inches by 4 inches. It's actually a little bit less than that. And so this is where we have a difference between the nominal size. So the nominal size is a size you see printed on the side of a product. It stems from the actual size, which is rounded up to the nearest whole inch. The nominal size given by a manufacturer is different from the actual size. And this is a short video that gives us a little bit of sense of that.
Is actually 1.5 inches by 9. Nominal dimensions are the green, rough, unplaned dimensions of lumber. Rough, sometimes also referred to as full cut rough, is defined as wood that is not dried or planed. The nominal dimensions are the common descriptors we use for lumber. These are some examples of the common 2x nominal dimensions and their actual dimensions. 2x2 is actually 1.5 inches by 1.5 inches. 2x4 is actually 1.5 inches by 3.5 inches. 2x6 is actually 1.5 inches by 5.5 inches. 2x8 is actually 1.5 inches by 7.25 inches. 2x10 is actually 1.5 inches by 9.25 inches. 2x12 is actually 1.5 inches by 11.25 inches. And here are some large number and smooth timber dimensions. 4x4 is actually 3.5 inches by 3.5 inches. 4x6 is actually 3.5 inches by 5.5 inches. 6x6 is actually 5.5 inches by 5.5 inches. 8x8 is actually 7.25 inches by 7.25 inches. These are industry standard dimensions used for design and planing purposes. Full cut rough lumber will typically be true to size, but you should always verify with your lumber or timber supplier if you aren't completely sure.
Okay, so just maybe a little bit of insight there, something that you can be thinking about. One of the ways to be thinking about nominal size versus actual size, rounding up. What is the number of significant digits that you're using? So here you see 1 significant digit. This is like 2. And so they're rounding it. So that would be one way of thinking about that. Here, now let's think about of a surveyor. So sometimes it can be out in some beautiful places around the country, around the world. Sometimes it's on roads, and you can see it's usually 2 individuals, one person with a device like this, and the other person that's down the road that's holding up something. And so they're trying to get their relationships between those two to get a good distance. So we want to explain the working of the instrument shown in the photo. And so far, we haven't had a chance to be exposed to this. And so I'll just go to this, and then I have a video that might give some insight, and then I'll pause and see if anybody has any thoughts as a result of seeing that. So the instrument sends out a light beam that is reflected by a system of reflectors located at the unknown distance. Thus, you see something with another person who's holding a reflector. The instrument and the reflector system are situated such that the reflected light beam is intercepted by the instrument. The instrument then interprets the information to determine the distance between the instrument and the reflector. So here's a short video, do-it-yourself land surveying, and giving us some insight into what's going on.
Seen these guys on the side of the road looking through fancy equipment on a Blue Apron for sponsoring this video. We're still in the process of getting settled into the new house. We use all kinds of measuring.
So I actually have a good friend of mine who is a civil engineer. So if any of you want to chat with someone that is in that specialization where surveying definitely comes to be more important maybe than some of the other ones, you can feel free to reach out. I'd be very happy to have you guys connect. Well, we have a couple other topics that we wanted to be talking about. And here we have these two different things. So with the surveying, you got a chance to figure out how you're determining size, change in elevation, things like that. And we got some insight to be thinking about how we do measurements and how we consider that in a couple of different ways. But now here's the first of two things is the radian. And so here radians represent the ratio of two lengths. And so they're unitless. And so here we can see the ratio of S1 to R1, S2 to R2, but those are going to be the same. This angle that is going between those would be the large. S1 is going to be smaller than S2, R1 is going to be smaller than R2. And so thus we can get some kind of relationships between different things as we're considering things from that point of view with the ratios and getting some use of radians. But here's another one that it's completely different, but this is definitely in the sweet spot for someone who's a mechanical engineer. There's something called stress, and then there's something called strain. Stress is where you stress a material, and then when you relieve that stress, it goes back to its normal state when it's under a load. So if you do it enough, it's actually going to strain, and it's actually going to deform the material, and it will never go back to exactly where it was before. And so that deformation, delta L is divided by the original length is called the normal strain, and it's given by this equation. I think I've seen the sigma is an example of one of the Greek letters that it can be used to represent that. So you can see how if you were to put this under strain, it's now has grown in length, and so the material in this the sample is actually changed. And here is a video. Have this and one other video that will be explaining this, but this is going to give you a little bit more an idea of this. You go in this region where it's linear, so this is where it's stress, but then here as you get strain, and it's no longer has the same characteristic of a curve.
The Efficient Engineer channel, everyone. In this video, we're going to talk about Young's modulus, one of the three main elastic constants, along with shear modulus and bulk modulus, which are used to describe how a material deforms under loading.
So some of these terms, maybe all of them are not familiar to you, but just try and the way that they do this in a visual sense, I think you'll at least get an idea of how this could be used for characterizing materials and its properties.
Let's introduce Young's modulus using the tensile test.
So the tensile test is basically you get a sample of material and you just start pulling it, and you record how much you have to put it under stress before it actually ruptures. And before that, you can see when it starts to get longer, and it varies in how much it changes over the amount of stress.
Test is a very common mechanical test, which takes a test piece and stretches it along its length. It is a uniaxial test, meaning that it applies a load in one direction only, as shown here. During the test machine measures the applied load and the change in length of the test piece. The main output from the tensile test is the stress strain curve, which describes how much the material we're testing will deform for different levels of applied stress. Watch how the stress strain curve evolves as we perform a tensile test on our test piece, which in this case is made of steel. The test ends when the material fractures. We can observe that the stress strain curve is split into two regions, the elastic region, where the curve is linear, and the plastic region. If the applied stress is low and we remain in the elastic region, the original dimensions of the component will be completely recovered when the applied load is removed.
So for a mechanical engineer and you're designing a structure, this is exactly what you want. You want to stay in this elastic region. So once that load is gone, it's going to go back to its regular length, but it can actually flex a little bit within this linear region.
Stresses that take us into the plastic region, permanent plastic deformation, will remain after the applied load is removed. In the elastic region, the stress strain curve is a straight line for most materials. This means the strain is proportional to the applied stress. Hooke's law gives us the relationship between stress and strain in this linear elastic region. The ratio between stress and strain is Young's modulus, also called the modulus of elasticity, which we denote with the letter E. It has the same units as stress, so PSI in US customary units and pascals in SI units. We can also measure Young's modulus as the gradient of the slope in the elastic region. Young's modulus is essentially a measure of how stiff a material is. The higher the Young's modulus, the stiffer a material, and so the smaller the elastic deformations will be for a given applied load. If we perform tensile tests for a few different materials, we will notice that the slope of the stress strain curve is different for each of them. Different materials can have vastly different values for Young's modulus. For anisotropic materials like wood or composites such as carbon fiber, the value of Young's modulus will depend on the direction in which the load is applied. This graph shows the range of typical Young's modulus values for polymers, metals, and ceramics. In general, ceramics have higher values of Young's modulus, metals have slightly lower values, and polymers have much lower values. Why is Young's modulus different for different materials? Understanding what is happening at the atomic level can give us a better understanding of Young's modulus. On an atomic level, a material's Young's modulus is closely related to the strength of the bonds between its atoms. We can imagine these interatomic bonds as tiny springs connecting adjacent atoms. Elastic strain is the result of an increase in spacing between the atoms of the material and is resisted by the strength of the interatomic bonds, or the stiffness of the little springs in our model. This is very different to the mechanism behind plastic deformation, which involves rearrangement of the position of the atoms. This is why elastic deformations are reversed when the load is removed, but plastic deformations are not. I mentioned earlier that Young's modulus is smaller for polymers than it is for ceramics and metals. This is because it is the weaker intermolecular bonds in polymers that determine the material's stiffness, rather than the stronger atomic bonds. Looking at things on the atomic level can also help explain why differences in Young's modulus for alloyed metals tend to be small. Let's take the example of carbon steel. Mild steel and high carbon steel have quite different mechanical properties. Their yield strengths, for example, are very different, and yet they have very similar Young's modulus values, which at first glance might seem surprising. We can explain it using our interatomic bonds model. Mild steel has a carbon content of up to 0.25%, and high carbon steels can have a carbon content of up to 0.95%. Adding such a small number of additional carbon atoms to the existing iron atoms isn't enough to significantly affect the overall resistance to increasing the spacing between atoms. And so the Young's modulus is very similar for mild steel and for high carbon steel, despite some of their other mechanical properties being very different. Why is Young's modulus important? Young's modulus is a crucially important material property when it comes to engineering. In engineering design, a common objective for many different applications is to keep elastic deformations as small as possible, which means that Young's modulus is a key parameter that needs to be considered in the material selection process. Take the example of a bridge. If we construct a bridge from a material with a low Young's modulus, it will deflect a large amount when something crosses it, which is probably not the desired response. Selecting a high stiffness material would ensure that elastic deformations remain small for large loads. That concludes this brief introduction to Young's modulus. Welcome back to the.
So hopefully, for those who are engineers, maybe that just encourages you to more. For those that are computer science, you can just take that in for some of the materials that maybe might be affecting the things that you'll be working on that could actually have some bearing to how things are going to be going on with your application. So the deformation divided by the original length is called what? Anyone want to take a guess on this one? I'll give you a clue. Stress is going to be reversible, strain is going to be permanent. Anybody have a guess what that might be the answer for this? Strain, okay, good. So normal strain is correct. So the deformation divided by the original length is called the normal strain. Normal strain occurs when the elongation of an object is a response to a normal stress. So anyway, so we're talking about length. We got a chance to, as a result, thinking about some of the things about the materials of things that we're measuring or using. Now let's talk about area, and then we're going to be talking about volume. But let's first talk about area. Area is derived or a secondary physical quantity. It is a length-related variable, plays an important role in the analysis and design of problems in heating and cooling, aerodynamics, cutting tools, and building foundations. And so for those that are doing programming, this would be something that would be part of your business logic. So it can be units of millimeter squared, meter squared, centimeter squared, kilometer squared, and so on. Or one of the things, if you've ever thought of an apartment or a house, let's talk about, at least here in the United States, I'll talk about what is the square footage of that house or apartment. Anybody have ever heard that term? You can do a thumbs up if you've heard that. Just give me a sense of if that's something you're familiar with. Okay. I've also been over to Europe and seen some of their advertisement. Instead of using square feet, they talk about square meters. And so for me, I have to scratch my head, just like they use centigrade. And although I'm familiar of the relationship from one to the other, I don't have an intuitive sense. Have been so used to using Fahrenheit for establishing temperature. It's something that can happen there. So area is useful. And we wanted to now start to unpack that a little bit. Think of the area calculations. And so the next chart we'll have in just a minute shows areas of common shapes, such as triangles, circles, and rectangles. And so we have formulas that are available for us, and many composite surface with regular boundaries can be divided into primitive areas. And so the second part is something that we're going to see in about 2 or 3 charts, but we can start to come up with a area calculation by starting to break it up into parts. So here are some things if you're given a size like this, and so we mentioned a soda can. Thus we can see the area calculation for this. It's not showing the volume, but what is the area of the outside? So how much material would be needed to create that cylinder at least the outside. That would be what we would have. You have a rectangle, probably the easiest, just the square is a more specific version of a rectangle, the height times the width. And these are just all some formulas that are there that you can be thinking of. A sphere, 4 pi r squared. And here we can be thinking of the approximation of a planar area. Some of you have had calculus and others will be having calculus. And this is just giving you an idea of what an integral does. What you do is you calculate what is the volume, what is the area below the curve. And so we can see the red is the real value and the dotted line is the approximation. So we can get fairly close. And as your delta goes to infinity, it's going to then be turning into an integral. So there are many practical engineering problems that require calculation of a planar area of irregular shapes. And so here we're using the trapezoid rule. So each one of these is divided into a rectangle with a triangle, right triangle on the top that we can be using for coming up with the area. So a bunch of rectangles and triangles, we can figure out to as much of an approximation as we want to calculate that area. Here's another example. So you could just be counted it into squares. And so and then you count the squares. You have some that aren't quite full. And so that would be where the approximation would come in. Another thing is you could have it be a rectangle, and then you come up with an approximation for each corner of how much you're going to subtract. And that would be another approach that you could be using for coming up with an approximation of a planar area. So subtracting the unwanted area, first fit large primitive areas around the unknown space and then approximate and subtract the unwanted small areas. So rectangle, and then you have a triangle that you subtract, and that would give you an approximation for that. The weighting of the area, the procedure requires the use of an accurate analytical balance from a chemistry lab. That's just something else. I'll just is something you can read more about in the textbook, but I'll just leave that for now. Okay, what is the area of a circle with radius 10 centimeters? Anybody want to venture a guess which one they think that would be? All right, C. And one of the things that is helpful, if you're familiar with the pi r squared, is what it is for a circle. Pi is 3.415926. Maybe you have some, maybe you've memorized pi. You don't have to, it's just readily available, but it's kind of handy to at least have that handful of digits. And so whatever that is that you are thinking of. And so here you can see that it's very clearly that this was the only possible answer, 3.15926. Let's see, that's here. This is a rounded number. Maybe you could argue for that one. But anyway, that's the number that we have. And so here we have the pi r squared. We have the number for pi, centimeter squared, and thus we get that value there. So I'm glad that people participated. It's nice to get a chance and feedback for what you're thinking on this. Well, now, not only are we thinking about area, we want to be thinking of volume. So this is another important physical quantity or physical variable that we use in our everyday lives to quantify the size of things. Volume plays an important role in how things are shaped and how things work. So cubic meters, cubic centimeters, cubic millimeters, cubic inches, cubic feet, and so on. And so buoyancy is another engineering principle where volume plays an important role. Force that a fluid exerts on a submerged object. And so we'll see that in just one more slide, but here are just some volume calculations that we have in our textbook. now we're getting the volume. So you think now we're doing the volume of the soda can rather than what is the area on the outside. All right, circular cone, the section of a cone. So you snip the top off of that, or a sphere or a sections of a sphere. These are just the equations that you can be using for that. Okay, well, let's have a discussion activity and get your thoughts. What is the principle of buoyancy? How do we use buoyancy in everyday life? Anybody want to share your thoughts on that? Or you can just put it in the chat. Either way, feel free to share. Anybody ever been to Salt Lake City and floated in the Salt Lake, or been to Israel and floated in the Dead Sea? Yeah, so buoyancy is used to keep us afloat in water. And so another thing is if you take a deep breath and go underwater, that most likely will be enough air that it's going to push you back up to the surface. And so thus we're seeing some things that are going on with buoyancy. So here I'm showing you an example. So the what's going on with the water. And then we have the boat actually is heavier than water, but it's just this hull in relationship to what's going on as it's in the water that's causing it. If you struck a hole, the water's going to seep in and eventually it would sink. So buoyant force on an object is equal to the weight of the liquid displaced by the object, where the density of the liquid multiplied by the submerged volume times the acceleration due to gravity. We're not showing an equation, so that may be hard to follow. A boat floating on a river, an iceberg floating on water, a person wearing a life jacket floating on water, a ship floating on the sea, and a helium balloon rising into the air are some examples of buoyant forces in everyday life. So we got some idea of what's going on there. Christopher wrote, the principle of buoyancy involves that the fluid pushes with an upward force against the ship, which has a downward force of gravity. And so that's what we got a chance to be seeing with this graphic here, to see it actually bobbing up and down. Well, here is another subject that it sounds kind of difficult to get your head around, but I have a short video that I think will help a little bit. And once again, for the mechanical engineers, you'll probably be eating this up. So this is something called the second moment of area. It's a property of an area, also known as the area moment of inertia. And so I'm showing that here. It is an important property of an area that provides information about how hard it is to bend something. So it's, you have millimeters to the fourth, centimeters to the fourth, meters to the fourth, inches to the fourth, or feet to the fourth. So the second moment of area, also known as the area of momentum, is a geometrical property that reflects how an area's points are distributed with respect to an arbitrary axis. It's crucial in structural engineering for calculating a beam's deflection and the stress caused by applied moment. So the next couple of charts, once you see the video, I think it'll make a little bit more sense, but how much you can bend. And so you can be thinking of a tube, say like you have some PVC pipe, some basically plastic, you can bend it to a degree. If it was metal, it's going to be a little bit harder. If you have another piece of structure, so you can see here, you're actually bending it in the thin axis and you're getting more, there's more ability for you to be flexing it, versus if you try to do it the other way, it's going to be a lot harder. So this is just some of the equations for a small area element A located at a distance r from the axis ZZ. The area of moment of inertia is defined by this equation. And this gets into the mechanics of material. And that's something for those that are taking the mechanical engineering track, you'll get a chance to be getting a little bit more into this. And there's equations for the area moment of inertia. And these are just some examples for a rectangle and a circle. But let me go ahead and play this video, and maybe this will kind of make it click for you, especially those that aren't an engineer, to see what I mean.
The further the material is spread from the bending axis, the stiffer a cross-section tends to be. The cross-section on the right has more material located far from the bending axis, and so is better at resisting bending, even though both cross-sections have the same area. This concept of resistance to bending can be quantified by calculating the area moment of inertia, which is also sometimes called the second moment of area. The area moment of inertia reflects how the area of a cross-section is distributed relative to a particular axis, and so is a measure of how much resistance the cross-section has to bending. The I-beam locates the majority of the material as far as possible from the bending axis, and so is a very efficient cross-section. This is what
So an I-beam, for those that are mechanical engineers, you can see the fact that you have this going in both directions. So in both ways that you might potentially be wanting, that it might be flexing, you have all of this material that's going to go counter against that.
is so commonly used in construction. In this video, we're going to take a detailed look at the area moment of inertia. Let's start by seeing how it can be calculated for an arbitrary cross-section like the one shown here. The first thing to note is that the area moment of inertia is not a unique property of a cross-section. It quantifies the resistance to bending about a particular axis, and so its value changes depending on where we place this reference axis. We can approximate the area moment of inertia of a cross-section by splitting it into small elements. Each element contributes to the total area moment of inertia by a quantity equal to its area, dA, multiplied by y squared, where y is the distance to the reference axis, which is the x-axis in this case. We can sum up the values for all of the small elements to obtain the area moment of inertia for the entire cross-section. It is denoted by the letter I, and because the x-axis is our reference axis, we will give it the subscript x. We can define the area moment of inertia more precisely using integration, like this. And if the y-axis is our reference axis, we can calculate Iy in the same way. The area moment of inertia has the unit of length to the fourth power, and because of the squared term, it is always a positive quantity. Let's work through an example where we calculate the Ix and Iy values for a rectangular cross-section using those equations. We can consider that the rectangle is made up of multiple thin strips, which each have a height equal to dy. Each strip has an area equal to b times dy, which gives us the following integral. The limits of the integral are from the bottom to the top of the rectangle, so from negative h over 2 to h over 2. If we solve this definite integral, we end up with Ix being equal to b multiplied by h to the power 3 divided by 12. We can obtain the equation for Iy by switching the height and the width terms. So there you go. We just calculated the area moment of inertia for a rectangular cross-section using integration. But calculating integrals can be difficult. So to help us out, area moment of inertia equations are often provided in reference text for a range of common shapes. A few examples are shown here. Usually the equations are provided for centroidal axes, which are axes that pass through the centroid of the cross-section. Remember that the centroid is the geometric center of a cross-section. XC and YC are called the centroidal axes. So what do we do if we need to obtain an area moment of inertia equation for an axis that is not a centroidal axis, but it is too difficult to calculate it using integration? Fortunately, there is a method we can use to calculate an adjusted area moment of inertia for any axis that is parallel to a centroidal axis, like this one. The adjusted area moment of inertia, Ix, can be calculated by summing the moment of inertia of the centroidal axis and the product of the cross-sectional area, A, and the square of distance d between both axes. This is called the parallel axis theorem. It's useful because we can take the equations found in reference texts for centroidal axes and adjust them to obtain the moments of inertia for any parallel axes. Let's look at an example. Earlier, we determined an equation for the area moment of inertia of a rectangular cross-section about an axis passing through the centroid of the rectangle. We can use the parallel axis theorem to calculate I for an axis shifted to the bottom of the cross-section. All we have to do is take the equation for I we derived earlier and add the area of the rectangle BH multiplied by the distance h over 2 squared. One useful property of area moments of inertia is that they can be added to and subtracted from each other. This means we can calculate the value of I for a shape like this by taking I for section A.
I'm gonna go ahead and not play the whole video because this is getting into a lot of things that we haven't covered and are beyond what we're trying to do and getting some experience in this course. But this is probably the main thing that I wanted to be pointing out was that here, if we had 100 kilograms, you can see how this this board is oriented. There's a lot more volume that's preventing it from bending versus this, if we go the other way, there's less. And so the amount of how much it's going to flex is going to be a lot greater. And so that's probably the main point that I wanted to have you guys think about for this concept. Any comments or questions on that, or give me a thumbs up if you're seeing this takeaway point that I'm trying to have you consider. Okay, and I know some of the engineers are probably eating it up, and that's perfectly fine. With a lot of variation of what we have for areas of disciplines and interest. I'm trying to sample a little bit
Let's say
for all of what you're doing. So I'll just go to the solution for this. We have what is the physical importance of moment of inertia? Moment of inertia has the same physical meaning as mass in a translational motion. The mass of a body is used to calculate inertia in translational motion. Inertia increases with increasing mass. The force required to produce linear acceleration also increases. For rotational motion, the greater the moment of inertia, the greater the angular acceleration. So let me just pause and I'll go back to the list of objectives and see if anybody has any comments or questions about this. Does this give you a little bit more sense of why length is an important thing for us to be aware of? Well, let's put this in the context of what we're going to be doing now. So we talked about the fundamental dimensions and systems of units. So we had a chance to be exposed to these: length, time, mass, temperature, electrical circuit, luminosity, amount of substance. And that's kind of, we're seeing that we're covering a lot of those topics as we go here. And so my goal is to try and figure out how to relate this both to engineering and computer science. This one was a little bit more challenging to be doing that, but as we get into next week, when we talk about time and related variables, some of what we spoke about on Tuesday, I think will be something that will relate there, and I'll continue to try and do that as we progress. One thing I would appreciate, just keep communicating with me if there are some particular topics that you think would be useful for us to cover as we're moving forward in the class. That would be both on the engineering side and the computing side. I would welcome your inputs. Okay. So let me pause and see if there's any other comments or questions that you guys have. And if not, I'll just say that that's probably a good breaking point. All right, well, you guys all have a good rest of your day. I'll look forward to seeing you next Tuesday. God bless now.